Good morning. I'd like to demonstrate to you the Grid Force 250 watt grid tie inverter. Now this is not, repeat not, your typical inverter that you might find in your car powering your laptop on a road trip. This guy has DC input. There's indicator lights down here that indicate whether or not you're operating properly. There's a fault light. There's a fan on this end. On this other end, there is an AC connection. There's a provided cord. You can set 110 or 230 volt operation. It's nicely done, and the case acts as a big heatsink. We've set up a couple of things. One is a pair of batteries from a UPS unit, which are wired in series so that the combined voltage is more than the input requirement of the grid tie inverter. That requirement is at least 14 volts, and we get about 25. The other instrument here is a power strip that's a kilowatt power strip, and it allows us to measure the watts being consumed or generated. First thing to do is to hook up our device, connecting the negative terminal first. I've already made these leads, preformed the ends, and tinned the conductors. These connectors are actually a little big for a banana jack. Ooh, sparks. Okay. Please note that the fault light is on and stays on. We are not connected to the line. One of the features of this device is that it does not operate if there is no line current that it can sync to. So the next thing we're going to do is plug it into the power strip. And we can see that the fault light has gone off. We now get blinking lights that go back and forth. The faster they go, the more synced up we are, and the more juice it's generating. We can hopefully see that we're generating over 230 watts of power. Now, the kilowatts power strip only shows an absolute value of the watts being consumed. We're not using watts, we're generating watts. 226 of them. Now, I'd like to do something in terms of efficiency. Using the voltmeter, measure the volts across here. We get 22.56 volts on the battery under load, and using a clamp-on ammeter, we measure 7.7 to 7.8 amps of current. Let's try the negative lead. Get about the same thing. I've now unplugged the inverter. The light bulb is nominally a 55 watt light bulb, and the kilowatt power strip shows it at 54 watts. If I plug in the inverter, we go back up slowly. Now over 160 watts. If I remove the light bulb, we go back up to where it's 230 watts. Now, let's, just for the sake of argument and demonstration, plug in a 500 watt light bulb. Now I'm going to do this without benefit of having our inverter plugged in initially. This is a 500 watt halogen spotlight that I've just plugged in. You can, quite bright, you can see it. And my kilowatt meter says 434 watts. We're doing an efficiency test here. I've hooked it up so that our batteries are running the inverter, and I've got 2 meters monitoring current on the left and voltage on the right. The kilowatt power strip is measuring about 197 watts. I've got it hooked up to a 500 watt halogen light that actually measures 434 watts when hooked alone to the kilowatt power strip. This should give us some idea of how efficient the device is by multiplying the voltage times the current in and measuring the watts out. This is an efficiency setup for the grid tie inverter. On the left, you'll see a fluke meter set up to measure the amount of DC amps coming out of our series connected 12-volt batteries. Again, the reason for that is that the grid tie inverter requires more than 14 volts. On the right is a voltmeter measuring the amount of volts of the series connected batteries. The kilowatt meter is feeding all its energy into the wall and shows 223 watts going in. So we're generating 223 watts with 12.2 amps and 24 volts. Based on our measurement, we have about 76% efficiency. Despite all our shenanigans, the grid tie inverter has yet to set off the GFCI outlet. That means it's producing good balanced current and shouldn't be any trouble in most household installations. One of the features of the grid tie inverter is that if it loses its normal nominal AC wall voltage, it will shut down and produce a fault and won't put any current into the wall. To test that, we're going to turn off the power strip. The fault light is now on, the red LED on the back of the unit, and we're not generating any watts according to the power strip. Also, our power consumption off the batteries has gone to nearly zilch. If I turn back on the power strip, we start producing watts, and the current consumption climbs on the DC side. Our fault light is off, and we have flickering green lights indicating normal operation. For a more visual demonstration, I'm going to plug in a light bulb. This is a 55 watt light bulb. We generate less electricity into the wall. Our net is our 200 and something watts minus the 55. Turn the power strip off, the light goes off, we don't consume any electricity. Turn the power strip back on, power consumption goes back up, fault light has gone off, and we're operating normally once more. Slowly it climbs. Here we are, we're all hooked up and ready to go. Remember, this type of inverter, this grid tie inverter, is not your typical inverter. If you take a typical inverter that you might use to run your laptop in your car and plug it into the wall, you will get smoke and flames. Somebody we thought was knowledgeable told us that you could do such a thing, and believe me, I wish I had that little experiment on video. I didn't believe him, but I tried it anyway. It's a good thing I had a fire extinguisher.